Welcome to today's paper reading. Today's paper is titled, MAGR, Manifold-Aligned Graph Regularization for Continual Action Quality Assessment. This paper was published on AR14 by Kanglei Zhou and colleagues from Beihang University and Tsinghua University. The abstract introduces Continual Action Quality Assessment, CAQA, which aims to refine models using sparse new data while preserving memory through feature replay. However, this approach faces challenges due to the misalignment between old static features and the dynamically changing feature manifold, leading to severe catastrophic forgetting. To address this, the authors propose Manifold-Aligned Graph Regularization, MAGR. MAGR aligns deviated old features to the current feature manifold, ensuring representation consistency, and constructs a graph that jointly arranges old and new features aligned with quality scores. Experimental results demonstrate that MAGR outperforms recent strong baselines, achieving significant correlation gains on multiple datasets, thereby validating its effectiveness for continual assessment challenges arising from non-stationary skill variations. Action Quality Assessment, AQA, goes beyond simple recognition to evaluate performance, but traditional methods trained on small datasets struggle with dynamically changing skills in sports and rehabilitation, necessitating updated standards. Continual learning, CL, offers solutions to non-stationarity but faces challenges like catastrophic forgetting. Continual AQA, CAQA, is introduced to refine AQA models using sparse new data without catastrophic forgetting, involving continuous quality score regression. Figure 1 illustrates the process of Continual Action Quality Assessment, CAQA, refining Action Quality Assessment, AQA, models using a few sequentially arrived instances without the need for exhaustive retraining. This approach advances continual learning, CL, beyond traditional classification tasks. The key points highlighted in the figure are that CAQA enables the incremental refinement of AQA models, utilizes sparse new data for updates, and represents a significant advancement in CL by addressing the unique challenges posed by continuous quality score regression. The Action Quality Assessment, AQA, evaluates the performance of actions across various domains such as sports and medical rehabilitation. It relies on deep learning models to improve performance over earlier methods that depended on handcrafted features. However, AQA faces challenges due to small datasets that risk overfitting and the segmentation of videos into clips, which limits a complete understanding of the action. To address these issues, continual learning, CL, paradigms are incorporated into AQA systems to ensure efficient adaptation. CL aims to train models over a sequence of tasks while retaining learned tasks and mitigating catastrophic forgetting. In AQA, CL focuses on few-shot learning to address severe overfitting and privacy concerns, particularly in sensitive domains. The novel task of Continual Action Quality Assessment, CAQA, is proposed to adapt to evolving individual skills or health conditions over time. This task is particularly challenging for traditional Action Quality Assessment, AQA, systems trained on static datasets. Unlike traditional continual learning methods focused on classification, CAQA involves continuous quality score regression, which is crucial for accurately capturing subtle variations in performance. This aspect is especially relevant in real-world scenarios where subtle variations in quality assessment can have significant implications. By introducing CAQA, the aim is to address this critical gap and provide a robust framework for continual refinement of AQA models in dynamic environments. The motivation behind MAGR is to address key challenges in CAQA by mitigating catastrophic forgetting through feature replay, improving adaptability by handling misalignment between static old features and dynamically evolving feature manifolds, and tackling misalignment through a two-step alignment process. The MAGR framework includes the use of ordered uniform sampling, OUS, to select representative features, the manifold projector, MP, to translate old features to the current manifold, and the inter-interjoint regularizer, IJGR, to align feature distributions. The training procedure involves careful parameter initialization, feature extraction and score prediction, and iterative model optimization to ensure convergence. Figure 2 illustrates the core concept of Manifold-Aligned Graph Regularization, MAGR. Part A shows the deviation of old features, blue circles, from the current feature manifold, orange curve, due to manifold shift. Part B highlights the potential confusion and score regression caused by the mixture of old features and current session features, green circles. Part C depicts the translation of old features from the previous manifold, yellow curve, to the current one. Finally, Part D demonstrates the readjustment of the feature distribution to align with the quality score distribution. This visual representation helps in understanding the two-step alignment process adopted by MAGR to mitigate catastrophic forgetting and improve adaptability in CAQA. Figure 3 provides an overview of the MAGR framework, detailing the process across two consecutive sessions, T-1 and T. At the end of session T-1, representative features are selected using ordered uniform sampling, OUS, and stored in the memory bank NT-1. During session T, the manifold projector, MP, translates old features to the current manifold, while the inter-interjoint regularizer, IJGR, aligns the entire feature space with the quality space. Old features are updated first, followed by the selection of new features for the updated memory bank, denoted as MT. Figure 4 illustrates the two sub-steps of the manifold projector, MP, across three consecutive sessions, projector learning and feature projection. Projector learning estimates the manifold shift at each model update using dependencies from the current session data. This involves replicating and freezing the encoder from the previous session to obtain initial features as a base for shift estimation. Feature projection translates old features to the current manifold by correcting each old feature from the memory bank. The inclusion of a residual link in feature projection enhances the effectiveness of learning through updates. The learning process of MP is supervised by minimizing the difference between predicted and actual updated features of the current session data. Figure 5 illustrates the fundamental concept behind our proposed IJGR module. It addresses the limitation in graph-based contrastive learning methods where Euclidean distance is commonly used to measure point separation within a manifold. This often fails to satisfy the geodesic property inherent in the data. To address this, we normalize features to fit a unit sphere and utilize angular differences for distance estimation. Additionally, we propose partitioning the distance matrix to effectively regulate the feature space. This matrix encapsulates dependencies from both previous and current sessions, ensuring a quality-aware manifold from both local and global perspectives. The CAQA benchmark is constructed using 4 datasets: Continual AQA, Fine Diving, UNLV Dive, and MSAJDM. These datasets cover diverse domains and scenarios to ensure comprehensive evaluation. The experiment protocol introduces a grade incremental setting, dividing datasets into subsets with equal samples, and training with limited samples per session to simulate real-world conditions. Evaluation metrics include Spearman's rank correlation, overall correlation AVG, and memory stability AFT, which collectively assess the efficacy of CAQA models. Figure 6 illustrates the grade incremental setting for CAQA, highlighting the dual challenges of classification and regression tasks. This setting involves discretizing the continuous quality space into distinct intervals corresponding to different action grades, ensuring an equal number of samples in each session. The interdependencies of non-stationary grades pose a new challenge for lifelong learning and preserving these dependencies to mitigate catastrophic forgetting. This approach creates a more challenging protocol for CAQA models to handle the variability in quality scores, allowing for a comprehensive evaluation of their adaptability to real-world scenarios. Figure 8 illustrates the challenges of label scarcity and noise robustness in the context of CAQA models. Part A shows the impact of varying the number of training samples per session on model performance. As the number of samples decreases, the model's ability to generalize and adapt to new data is tested. Part B examines the effect of different levels of label noise on the model's performance, highlighting the robustness of MAGR compared to other methods. Parts C and D provide correlation plots at a noise intensity of 9, comparing the performance of NCFS-CIL and MAGR. These plots demonstrate that MAGR maintains a higher correlation between predicted scores and actual ground truth, even under significant noise conditions, underscoring its superior resilience and effectiveness in real-world scenarios with limited and noisy data. The experimental setup for training the models involved using PyTorch on two NVIDIA RTX 3090 GPUs. The optimization was performed with the Atom Optimizer, with a learning rate and weight decay both set to 10 to the power of -4. The training process spanned a maximum of 50 epochs, with a batch size of 5 and a mini-batch size of 3. To compare the performance of MAGR, it was benchmarked against a series of memory-free and memory-based baselines, with detailed results provided in Table 1. The primary metric considered for evaluation was AVG. Key findings from the experiments indicate that MAGR significantly outperforms all compared baselines, effectively addressing the issue of feature deviation and demonstrating superior performance in the context of continuous action quality assessment. Figure 7 illustrates the impact of memory size on the performance of replay-based methods in the MTL-AQA dataset. The graph shows that MAGR maintains its resilience and performance within the range of 5 to 11 features per session, thanks to the integration of the OUS module which samples representative features efficiently. However, when the number of replayed samples per session is reduced to 3, MAGR's performance notably degrades. This decline is attributed to the OUS potentially sampling extreme boundary samples that fail to effectively maintain the old distributions, suggesting that random sampling might perform better in such constrained scenarios. The figure underscores the importance of a balanced memory size to ensure optimal performance in lifelong adaptation tasks. Figure 9 presents visualizations of feature distribution and score correlation, comparing MAGR and feature MER methods. Panels AF show the feature distribution across different sessions, highlighting MAGR's effectiveness in organizing samples coherently. Panels GH depict the score correlation plots, demonstrating MAGR's superior correlation between predicted scores and actual ground truth. This explicit division of sessions validates MAGR's capability in mitigating catastrophic forgetting, as opposed to feature MER which struggles with feature deviation. Figure 10 presents a qualitative comparison of sample number 176 across different sessions, AD, and the outputs generated by feature MER, E, and MAGR, F, on the MTL-AQA dataset. The reparameterization trick, 48, was employed to predict the score, with insigma denoting the mean and standard deviation, respectively. This figure highlights the differences in performance between feature MER and MAGR, particularly in maintaining alignment with the ground truth score. MAGR's prediction remains within a margin of 2 points from the ground truth, indicating a closer alignment compared to feature MER. Table 1 presents the experimental results for various CAQA models, focusing on the primary metric AVG. The table compares the performance of our method, MAGR, against a series of baselines, including both memory-free methods and memory-based approaches. Key performance metrics such as AVG, overall correlation, AFT, average forgetting, and ROFWT, forward transfer, are used to evaluate the models. The results highlight the superior performance of MAGR in addressing feature deviation and mitigating catastrophic forgetting in the CAQA setting. Table 2 presents the results of ablation studies conducted on the MTL-AQA dataset to understand the contribution of each module. The first row shows the performance of the entire model, MAGR. Each subsequent row details the impact on performance metrics by removing a specific component. Removing the MP module results in a significant drop in AVG by 23%, highlighting its crucial role in feature deviation rectification. The exclusion of the IJGR component affects AFT by 452%, emphasizing its importance in maintaining regressor alignment across sessions. Removing the OUS component impacts ROFWT by 46%, indicating its role in efficient exemplar selection for replay. The study collectively verifies the importance of each module in achieving the model's overall performance. The conclusion of this work highlights the novel task of CAQA, designed to handle real-world complexities while mitigating catastrophic forgetting and prioritizing user privacy. To address these challenges, the authors propose MAGR, a solution that integrates MP and IJGR to iteratively refine old features and regulate the feature space across incremental sessions. Future research directions include exploring more robust network designs, optimizing the number of layers, and investigating advanced architectures like FIT. Additionally, incorporating prompt-based techniques could ensure parameter-efficient tuning and enhance adaptability. Thank you for watching.